Okay, so when we last left off, I promised you that I would be presenting you a much nicer diagram of an HPLC. And so this is what I've drawn here, okay? This area here is the solvent reservoir. Usually there's about 4 solvent bottles. Sometimes there's only 2. But this is our mobile phase reservoir. And those are either under pressure and filtered, or they are degassed later on, and they feed into a proportioning valve. Okay, um, that proportioning valve will open for certain amounts of time to make sure that uh, the mobile phase concentration settings that you have from the computer, uh, which is over here, are in effect by the time the mobile phase reaches the pump head. Okay, so say you have solvent A at 50%, solvent B at 50%, the proportioning valve will have solvent A open for 50% of the time, solvent B open for 50% of the time, and it'll just switch back and forth between the two. Most proportioning valves can have up to 4 mobile phase constituents plumbed in, and that will output to a degasser, or sometimes the degasser isn't there at all, or sometimes the degasser is immediately after the eluent reservoirs before the proportion. Okay, um, that will then feed into the pump heads, which are designed in the way that I drew from the last video, right? The reciprocating pump heads, and those reciprocating pump heads will output the degassed proportioned mobile phase to the pulse dampener, okay? And the pulse dampener also contains a drain valve and additional filtrations, and an outlet for our priming syringe in case of manual priming for the pump. This whole system, which I've outlined in blue here, is all housed in the pump for an HPLC instrument, okay? Typically, you will have the pump, underneath your eluent reservoirs, so that once you get flow starting from the eluent reservoirs to the pump heads and out, that flow will continue until a break of gas, an air break, gets into the line of the mobile phase reservoir bottles. Okay? From there, we flow into the injection valve, and we'll be taking a detailed look at the injection valve later, but the injection valve has one input for the pump flow, one input for an injection flow. Okay, and then there will be 2 ports that you connect with an injection loop. We'll go over that later as well. And then an outlet port that will go to waste. Okay, so whenever you do your injection, you actually inject so much sample that you overfill this injection loop, and you watch excess come out the waistline. That's how you know the injection loop is full and that there's no air bubbles in it. Okay, and then there will also be an outlet to the column system. So that is 2 inputs, 2 outputs, and 2 lines for the injection valve. So at minimum, there are 6 openings in an injection valve. Okay, and at any one time, 3 of them are connected together. All right. After the injection valve, you see the guard column, typically in HPLC systems, and this is, just as it was in GC systems, meant to prevent things that would otherwise damage the analytical column from reaching the analytical column. Okay? It is considered a consumable device. It is sacrificial. These are typically on the order of 5 centimeters in length, as opposed to the analytical columns, which are typically 25 centimeters in length. And when you have this just this guard column on line, you should not see a huge amount of back pressure because these are fairly wide bore. Whereas the analytical columns are typically much more narrow bore, they're longer, and they will generate significant back pressure. Okay, um, back pressures at minimum of around 900 psi are common. Then the analytical column will outflow to the detector. Now, this piece of tubing right here is very important. You want to make sure that you keep this piece of tubing, as well as all the rest of these, as short as possible, but especially this one. Okay? This must be as short as physically possible. And I want you to think about why that could be and post it in the comments below, based on what you know about chromatography. Why would we want this after the column? Why would we want this line here to be as physically short as possible? Then we go into the detector, and from the detector we go to waste. Sometimes you can go into fraction collection. There are automatic fraction collectors out there that will take the UV vis absorbance, and it will use that to trigger fraction collection. Okay, and all of these things are interfaced via data lines that I've shown here in dashes in dash lines to a PC. Okay. All right. Okay. So now that we've discussed that, let's talk about the injection valve. Okay. So most often, the limiting factor in HPLC reproducibility for a sample is how a sample is introduced to the column. Okay. Um, so sample introduction is often the limiting factor in method reproducibility. Okay. As a result, we use small volumes. Okay. And we try to introduce it as a plug. Okay, a nice tight plug. So it's very much like cold focusing in a GCMS, right? We want to concentrate the sample as much as possible in the instrumentation. We don't want it to be taking up a whole lot of room. All right. And so for this, we use an injection loop. Okay. And injection loops are very clever devices. All right. They are known volumes of tubing. Okay. And so let's do a real quick exercise, right? If we wanted to create a 100 microliter injection tube or injection loop, and we didn't have any on hand that we had purchased from VWR, maybe because our PI doesn't have any money, right? We would have to make our own. And the only thing we have on hand is 0.0025 inch ID tubing. How could we do that? Well, we can say that we need 100 times 10 to the minus 3 centimeters cubed, right? That is 100 microliters, right? To be equal to pi times r squared times L, right? Where r squared is going to be the ID of the tubing over 2, right? So the only real variable that we're not in control, that we can, control here is L, okay? And I would like for you to solve for L, all right? The first thing you're going to have to do, though, is convert this from inches into centimeters. So take a few minutes and do that. All right. Now that you've done so, we're going to go over an injection valve. Okay. So injection valves have at minimum 6 ports if they're not more complicated than that. They're usually arranged in a pattern like this, and they have 2 settings. They have load and they have inject. Okay. And again, it's that kind of honeycombed hexagon pattern. Okay. And what we do is we number them. Okay. And they're usually numbered on the back. Okay. And typically, you will have your injection inlet at port 6. Okay. And in the load configuration, 6 is connected to port 1, 4 is connected to port 5, and 2 is connected to port 3. Okay. If we put our injection column or our injection loop over ports 1 and 4, then when we inject in, we'll have excess go to waste out of port 5. Okay. But what about ports 2 and 3? Well, port 2 and 3 would be our column flows. Okay. So when we're in the load state, we bypass the injection valve, the injection loop on the pump flow. Okay. And we pump directly to the column. All right. Then when we swap this over to inject, okay, our connections swap. All right. Our internal connections. So the pump in is still there at port 2, but now port 2 is connected to port 1, which connects across the injection loop to port 3, which is still connected to the column. And then ports 5 and 6 are directly connected so that you can flush your injection line. Okay. All right. So those are the 2 states of an injection valve. Okay. Take a note that first we fill the loop and then we flush it with the pump. All right. So just keep an eye on that. Just think about that for a minute. Okay. You may wonder about the name. Well, load is for loading the sample into the injection loop. Inject is for actually injecting the sample into the instrument. All right. Okay. moving on. Let's talk about detectors. Okay. HPLC detectors will vary based on the chemical properties and physical properties of the sample. Okay. So, for example, UV vis with a flow cell is common, okay, is common, but it would be inappropriate if your molecule didn't absorb UV light. And you may be wondering, well, how could we have a UV vis flow cell? Well, it's actually much easier than you might expect. Okay, so essentially what we do is we have a narrow pathway that goes between two windows. Okay, I've drawn this really poorly, and that's supposed to be my eraser. I've drawn that really poorly. Let me try that again. Okay, so on one side you've got your inlet, and then on the other side you've got your outlet, and that is housed in a large block for mechanical purposes. Okay, and then on either end are quartz windows. Right, we have our UV source on one side, and we have our photomultiplier tube on the other. Right, so material can flow in, and then it flows out. All right, basically how they work. Right, but again, UV vis would only be appropriate so long as our actual analytes absorb in the UV. Right, we can also get, or in the visible, if in the case of a visible flow cell. Okay, we can also have, instead of a photomultiplier tube, we can have what's called a diode array detector. Okay, and diode array detectors actually have multiple wavelengths. That they can analyze. Okay, you can actually set them to say, okay, I want this wavelength at this sensor, this wavelength at this sensor. And your instrument can say, okay, well, at this diode I'm seeing this, and that, because the radiation here is being separated based on wavelength after the fact. Okay. Um, Another one is fluorescence. But again, it would be inappropriate to use a fluorescence detection with this flow cell setup um, with a molecule that doesn't fluoresce, right? You need your analytes to be fluorescent. Fluorescence is often used for proteins. Okay, it's often used for proteins because 3 of our 20 essential amino, or our 20 standard amino acids are natively fluorescent. Okay. In addition to these two, okay, you have mass spec. Okay, you can have mass spec detectors, and we discussed those. Those are usually interfaced by electrospray ionization, okay, to the mass spectrometer. All right. Other common detectors include electrochemical. Okay. And so you can have detectors that do reduction and oxidation. You can have electrochemical detectors that just work on conductivity. All right. Um, each one of these is designed for a particular set of analytes. All right. In general, we can break these down into two categories, right? UV vis and conductivity detectors are what we would call bulk property. Okay? It's not dependent on any particular chemistry of the analyte. All right? It is based on the properties of a bulk. In fact, UV vis you can use with pretty much anything because you can use the UV to observe changes in the refractive index, which is proportional to the amount of stuff dissolved in your solvent. Okay. Um, there's also density detectors that work in that way. Okay. The rest, the rest are considered solute property detectors. Okay. So bulk property are things like refractive index, density. That's not rho, that's delta. Density, uh, thermal conductivity in GC, right? But conductivity, right? Whereas solute property detectors are like UV absorbance, uh, visible absorbance, fluorescence, redox. Okay. Those are solute property detectors. They are dependent on some chemical property of the analyte. Okay. So ideally, HPLC detectors have 8 characteristics. First, they should be adequately sensitive. All right, to the task being done. Right, we need them to be able to detect the analyte. You wouldn't use a detector that can't go down to 2 parts per billion if you know your concentrations are going to be in the region of 2 parts per billion. That would mean that you would need a mass spec, right? Um, whereas if you know that your concentration can be as high as, say, 2 molar, UV vis might be fine, right? They should have good stability, and reproducibility. Because remember, we're not just measuring um, the property once and being done. You know, it's not like doing a UV vis experiment with a spectrophotometer. We're not just putting in a cuvette, measuring the absorbance, writing it down, moving on. We're actually constantly monitoring it. So we need that signal to be stable over time. Okay? If the detector signal is at baseline is constantly jumping around, it's going to make it impossible for us to actually perform any chromatographic analysis. Okay? We need a linear response over several orders of magnitude. Now, This one is becoming less important as we get more and more techniques for proper nonlinear calibrations, but it's still a good thing if we have a linear response with a wide working range, um, because linear least squares regression is much easier to perform than a nonlinear calibration or a nonlinear regression, and it's much easier to use as being accurate. Okay, they should have a short response time. Okay, we should be able to see changes in the eluted solution very quickly, but we also need it to be independent of the flow rate. Okay, because we don't want the detector response changing if the flow rate moves up or down a little bit. Okay, we don't want it to be sensitive to the pump. Essentially, is what we're saying, right? Should be very reliable, so it should have a high degree of reliability. And it should be easy to use. Okay, you shouldn't need to sacrifice a chicken and spin 4 times and tap the top of your head and say a magic chant in order to get the detector to work every 10 seconds, right? This thing, the detector should be able to just constantly work after you flip the on switch, and that's it. Okay, so, and they need to be reliable. We need to be able to know that halfway through a run it's not going to fall apart, right? So these things can't be held together by hopes, prayers, and bubblegum. All right. We need a similarity in response. To one or more classes of solute. Right? Think about a UV vis detector. That's good for anything that absorbs in the UV or visible range. Right? A conductivity detector is good for anything that can carry electric charge. Right? Mass spec detectors, fantastic for anything that can be ionized. Right? We don't want it to be, this can only detect this one particular analyte in a very narrow range of concentration and only sometimes when the wind blows from the wrong direction, right? Or the right direction, as the case may be, right? Ideally, our detectors will also be non-destructive. But wait, this seems to exclude mass spec, right? Seems to exclude mass spec. Why is that? Well, really, whenever you do ESIMS or any kind of LCMS, there is a large fraction of your sample that actually gets thrown away at the entrance to the mass spectrometer. You can collect that, okay? So the mass spectrometer still meets our criterion of being non-destructive, though less so than, say, something like a UV vis detector. Redox detectors also meet this criteria despite reducing or oxidizing our analyte, because we can always reverse that electrochemical change if we employ the right chemistry, right? And we want these things to be functional, okay, from room temp to 400 degrees C. Okay. Now, 400 degrees C is the cutoff for GC, right? Um, for ion chromatography and reverse phase HPLC, the temperature would never exceed 100 C, so we want it to be functional at least to around 100 C. right? Because if we go above 100C, we'll explode the system, right? And in normal phase, right? In normal phase HPLC, that temperature could be even lower, right? Because we don't want to go over uh, the boiling point of the mobile phase. Okay, so it's something you have to keep in mind. All right, 400 degrees C is the rule for GC, though. If you want something to be a GC detector, you need it to be able to function at 400, up to 400 C. Period. Period. Okay. All right. How long have I been yammering at you? Long enough. Well, no, let's finish this up real quick. There's only a couple more things to talk about, so you get a long video today. If I can clear the canvas. Stop hoping I can't clear it. Okay. So, now it comes to selecting a column. I want you to take a couple minutes. Go to Thermosite or go to Phenomex or go to Shimadzu or Shodex or Metronome. Okay, look at look at the number of GC and LC columns they have available. There are a lot of column choices. There's a lot of column choices. So how do we narrow it down? Well, first, we have to look at what kind of chromatography are we doing, right? If we're doing cation exchange chromatography, then we need a cation column, right? Same thing with anion exchange, right? So sometimes it's that simple, right? The very first thing you have to do is select what kind of chromatography am I doing and choose a compatible column. Okay. Second, you need to look at what mobile phase will you use. Okay. Because then you need to ensure compatibility with that mobile phase. All right. Then the next question you ask is how will the matrix interact? Okay. In an ideal world, you shouldn't need to do any sample prep. You should be able to take your whole sample and just inject a bit of it on, maybe do a dilution at most, right? And just inject that in your instrument and get an answer in an ideal world. Okay. In reality, it's usually not so simple. There's usually some steps you need to do, at the very least filtering along with dilution. Okay. But you need to look at how your matrix is going to interact with the column and then choose, of the narrowed down list, right, a compatible column from there. So we go from a huge number of choices, right, down to one or two. Okay. Right. And by the time we get down to these one or two, that's when we start asking about things like budget. Because sometimes the difference is a couple $100s, right? Sometimes the difference is you need a column that will work for more than just this one particular separation you're trying to do. And so you want to try and find one that overlaps with another separation that you're trying to do, right? So those are some guidelines when it comes to selecting a column. All right. All right. So that about sums it up for HPLC. I think I will do one or two more videos on more specific techniques, specifically on supercritical fluid, on ion chromatography, and talking a little bit more in detail about those. And then I think I'll maybe talk a little bit about stuff that is maybe less common that you might run into, like capillary electrophoresis, so that you can understand how those work. All right. See you then.